All right, now we're going to talk about bases. We've already done acids, and so what's a base? Well, a base is the opposite of an acid, and we're going to see why in just a minute. But before we do, let me just remind you of the water dance. So water molecules, and we have put a 2 here for the balancing. Whoops. When they bump into each other, they make H3O plus and OH minus. And they do this little dance in what's called a dynamic equilibrium. So actually the arrow, I better fix that arrow. It's a dynamic equilibrium. And so what we do is we draw an arrow that sort of goes both ways to show that water can turn into hydronium and hydroxide, but then also in the same cup, when everything's juggling around, hydroniums and hydroxides will get back together and form waters. And it's just this back and forth that's going on inside. And the key for water is that there's always the same number of H3Os and OHs, hydroniums and hydroxide. They balance out in this dynamic equilibrium. So there's no overall effects. And we say that water is neutral. This is what makes water neutral. Okay? In the last video, we saw that if you add chemicals to the water that have hydrogens that can come off, those hydrogens can also add to waters and create more H3O. So this goes up and it throws off the balance. So an acid is something that increases the amount of hydronium ions in the water and messes up the equilibrium of this little dance. It's no longer neutral. We say that it's acidic. Acidic. Well, obviously you can kind of guess that the opposite of an acid would be a chemical that somehow, instead of making H3Os rise in numbers, something that creates hydroxides to rise in number. That's what bases do. Bases somehow, as we're going to see, produce or create extra hydroxides that throw the balance out in the other way. They throw out the balance in favor of the hydroxides. Now there's 2 ways you can do that. So why don't we put that down? A base is a chemical that can increase the amount of hydroxide ions. So acids make hydronium ions, bases make hydroxide ions in a solution. Now, how do they do that? Well, there's 2 ways that this could happen. One of the ways it can happen is if they happen to have hydroxide ions in them. So one of the easiest ways to see a base is to look for hydroxide ions. And, so for instance, NaOH, we call that sodium hydroxide. Well, if that goes into the water, so we put sodium hydroxide and we dissolve it in water, there's my AQ, so now it's dissolved in the water. Then what happens is the water pulls apart and we get the sodium ions surrounded by water, just like before. And then we get hydroxide ions that are surrounded by water. And since they're all still surrounded and dissolved in the water, we put little AQs beside them. So the water has broken it apart. And what's important is that these hydroxides will be extras. They won't be from the water dance. They won't be just from 2 waters doing their thing. They'll be leftovers or extras who don't have a partner. They don't have a hydronium to get back together with. So they start building up in the solution as excess. All right? So excess. In fact, increases the amount of hydroxide, or I think if we use the same language as we did in the acid video, it's a chemical that causes an excess of hydroxide. So there's sodium hydroxide. Magnesium hydroxide can do the same thing, right? It has two hydroxides, AQ. So when you put it in water, you have to imagine what the water can do. It has its polar sides. The oxygen side is a little bit negative and the hydrogen sides are a little positive. So when this floats in the water starts to pull on these ions and it pulls them apart, right? It dissociates them. Remember from the video we did a few days ago? And it produces magnesium ions that are 2+ that are all surrounded by water. And two hydroxide ions. We have to balance it with 2 hydroxide ions. So anything can do this. Magnesium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, iron 3 hydroxide, tin 4 hydroxide, anything that has that hydroxide ion in it, as long as it's able to be released. There are bigger molecules, big ones that have many atoms, and there are some hydroxides in them, but they don't release as easily. So they don't actually make extras. They just kind of get floating around and they don't do this. But these smaller ones, these ionic ones, are pretty much all capable of splitting apart and creating an excess of hydroxide ions, which drives that up. And it disrupts the equilibrium of the water dance. Now here's another way, though, that you can get hydroxides. Let's imagine, so there's one way, just having hydroxide in the molecule. But watch this, there's a molecule called ammonia. Ammonia, if we draw its picture, it's got a shared H in 3 places, but it also has 2 little electrons here that weren't doing anything. Now remember, so does water. Remember what water did, right? Water has an oxygen with these little electrons here, and what it was able to do was when a water molecule came by, another one, this little H left his electron behind, he becomes H+, and then he joins up over here. He joins with the other water, and he made hydronium, remember that? And what he left behind was an OH, a hydroxide. That's the water dance. And it happens because an H from another water is attracted to those 2 little electrons that are there. Well, look at nitrogen here. He's got 2 little electrons here as well. And if a water comes by, let's put a water here. The hydrogen in that water may say, oh, I'm going to leave my electron behind. Oxygen can have it because oxygen's hogging it anyway. Right? I hardly ever get it. Remember, it's not a very good share, is it? So he's like, the heck with that, and he'll come over here and he'll join up with this ammonia molecule. And then what that makes is an NH4 with a plus, because remember that H left his electron behind. He's not bringing it with him. But here, we have the OH minus. So it's very much like the water dance, except there's one key difference. There's no hydronium. This is not hydronium. This is an NH4 ammonium. Ammonium. That's got nothing to do with the water dance. And so what we're making is we're making hydroxides without making any hydroniums. And that means that the hydroxides will build up in the solution. And there won't be enough hydroniums from the water dance to cancel them out. And they'll start to build up as extras. So ammonia can become ammonium by stealing an H from water, which then produces hydroxide floating around in the water. So we can write this as sort of like an equation. Let's see. We could write ammonia, NH3. I'll put the AQs in a minute, plus water, because it's actually interacting with the water, right? And this would sort of be an equilibrium too. This is kind of like the ammonium dance. But the ammonium dance, because obviously if an NH4 is floating around, it could find another water, or find an OH, and give it back. But what you get is NH4 plus and OH minus. And of course, all of these are dissolved in the water. So we have to put a little AQ beside each one to show that they are, well, water itself isn't really aqueous. It is water. So usually we put an L for liquid there. But all the other molecules we show are dissolved in water, like that. And of course, if we try to balance this, it's a little tricky to balance, right? Because you have 3 hydrogens and then there's 2 hydrogens over here, because every hydrogen is being pulled over to the ammonia. So let's think about this. If we put a 2 here, that'll give us 6 hydrogens plus 2 is 8, right? And if you think about it, this will make 2 hydroxides, and then we get 2 of those. I think that will make it work. So now we have 2 N's, we have 8. Did I do that right? Yeah, I think so. 3, 6, 7, 8, 8, 9, 10. Oh, wait a minute. Yeah, I just realized as I'm thinking this through, we don't really need any 2s at all, because it's going to balance. I got 2s overzealous there, and I thought we had to balance. It already is balanced, if you think about it, because there's 5 H's here. Oops. There's 5 H's here, but there is 5 H's here, right? Because the OH has 1. So everything is balanced nicely already. So we don't even need any balancing numbers to make this work out. But notice something. This little dance is producing hydroxides, but it's not producing any hydroniums. And of course, with acids and bases, it's all about the balance between hydroxides and hydroniums. So this would produce more hydroxide, even though it doesn't have any hydroxide in it. It can do its own little dance and pull off hydrogens from water and make hydroxides. So this ammonia is also known as a base because it can do this. So there's 2 ways that you can make hydroxides. One is just to have hydroxide in there and it pops off because the water pulls on it. The other is to be able to have extra little pair of electrons like this that is strong enough to pull off an H from a nearby water and make hydroxide without making any hydronium to upset that balance. Okay, common bases. Common bases. Bases don't really have as complex a naming system as acids, because a lot of them are just chemicals that have common names, right? And so, for instance, the sodium bicarbonate, NaHCO3, that's baking soda, sodium bicarbonate. And we all have this in our cupboards, bicarbonate, that's baking soda. And we're going to see, when you start to react acids and bases together, we're going to see why this baking soda is a good thing to bake with. It has a very specific purpose when you bake. It essentially releases a gas that causes your batter to get all bubbly and soft, so it makes like a nice fluffy cake or something. Ammonia, as we saw before, NH3. Ammonia. Remember, you have to keep clear in your head. Ammonium. I'm writing that by mistake. Ammonia is NH3. Ammonium is what it becomes in its little dance after it pulls an H off of water. Ammonia, a very strong base. Bleach. Bleach is a very strong base. Bleach is usually made with a polyatomic ion. It's usually sodium hypochlorite. Sodium hypochlorite. We won't worry about the, well, I guess we could, right? Remember chlorate. So sodium chlorate is ClO3, chlorite is ClO2, and hypochlorite is ClO. Remember that? So sodium hypochlorite. That's what bleach is. And it has the ability to pull H's away from water molecules, kind of like ammonia does. And these are all things, you'll notice that a lot of the things that are bases we use for cleaning products, right? Toilet bowl cleaner is a strong base. And that's because most of the things that make up dirt and stains are usually made by acid-based, or acid molecules. Stains, right? Like tomato juice is very acidic, it has acid in it. And so if you want to eliminate or neutralize a stain, the best way to do it is with a base that can neutralize the acid, but we'll get into those kinds of things later. So that's really all there is to say about bases. We'll see them as we go. We'll introduce ourselves to different bases. A lot of the ones we will use are just the ones that have hydroxide in them. So anything hydroxide, right? So anything hydroxide. I'll use the star there. Sodium hydroxide, magnesium hydroxide, and iron 3 hydroxide, lead 4 hydroxide. Those all can give hydroxides, so they obviously are bases too. So whatever, anything plus a hydroxide is also usually going to be a basic kind of chemical. And that's what bases do. So they increase the hydroxide ion in the water, whereas acids increase the hydronium. You notice there's no hydronium here being created in either one of these cases. So that means it's not a balance. If you're only making hydroxide, you're making you're upsetting the balance of the water dance. Okay, so that's where we'll stop for now on that.